So recall that before we started proofs, we started looking at logic so that we could think in a logical manner when formulating arguments in proofs. So the fundamentals of logic is basically truth values, breaking things down into simple statements that you can determine whether or not those statements are true and false. And then we had a few more complicated statements, which is combining some basic statements in specific ways with specific set of rules. So here we have statement P and a statement Q. These are logical letters that can represent anything from P being it's sunny out and Q being there are clouds in the sky. So we can see that we can test all possible truth values for P. When P is true and Q is true together, only P is true and Q is false, P is false and Q is true, or both are false statements. So we can look at these different, more complex statements using these rules that we developed. Recall that this symbol represents a conjunction. Conjunction is basically representing the word and. Is P and Q true? Well, those would only be true when they are true together in this first statement, and false in all the others. Here P is true and Q is not true, so that statement would be false, that both are true. So that's what the truth values would look like for that. Here we have a disjunction, or an or statement, which would be true when either P or Q is true. So these would be the truth values that go with that. Remember that this or is an inclusive or, so it's P or Q or both. In any of those situations it's true, in others it's false. Here's a conditional statement, which is an if-then. If P is true, then Q would follow. And the truth, or the question we would ask in determining that truth value was the broken promise rule. This statement is true as long as I don't break my promise. So I promise that if P, then Q. If P, then Q. Well, here we can see that it's true. If P, then Q, well, in that case I broke my promise. I promised that if you did P, then I would do Q. And I didn't follow through my word, so I broke my promise there. But in all the other situations, you never lived up to your end, so this is situations that we call vacuously true. So the truth values look something like this. If I keep my word, the statement is true. If you never lived up to your end of the bargain, I was truthful in my statement, but my statement was never actually tested. It's called vacuously true. And then we are at last statement, a if and only if statement, or biconditional statement, is basically implying in both directions. So these will have, this will have a truth value of true whenever both statements are true together. So we have this situation. So now, how do we use these types of rules in actual logic statements? Well, an example of that is right below here. Given that P is true and R is false, state the truth value of the following. Well, we can test these by kind of filling in their truth values and then refer back to this table. For the first, we can see that P is a true statement and recall that this little tilde means not. So this would be not R, because R is false. If it's not false, then it would also be true. Well, true and true, in a conjunction, true and true result in an overall true statement. We can repeat this process for each of the other conditional statements. Not P, well, P is a true statement. Not P would be false. Implies, but notice that for conditionals, whenever my hypothesis is false, the statement is always true. It's vacuously true. So I don't even have to consider what the second part is. I know immediately the statement will be true. And the last one, P is a true statement, not R. If it's not false, it would be true. So since they share the same truth value, for a biconditional statement, it will be true overall as well. So it turns out all three of those statements happen to have a truth value of true. So the truth value is just whether or not the statement is true or false. Looking now at our laws of inference, how we've used this logic. We have the three main laws: law of detachment, law of contrapositive inference, and law of disjunctive inference. Law of detachment is basically when I'm detaching off that conclusion. If P, then Q follows. Well, I know that if this hypothesis happens, then the conclusion is also happening. I'm kind of detaching it off as the conclusion itself. Law of contrapositive inference, remember that there are those 4 related conditional statements. These are them. When I have a given statement, if P then Q, I have an inverse, which is the negation of both sections of that statement. The converse, which is when the hypothesis and the conclusion have interchanged positions. And the contrapositive, which is when they are negated and switched. Recall that the only statement of these 3 related conditionals that is logically equivalent or shares the same truth values as my original statement is the contrapositive. So an original conditional and the contrapositive share all the same truth values, or they're saying the same thing. Scrolling back down, the law of contrapositive inference is basically an application of that, which is if I know the conclusion does not happen, then the hypothesis must not happen either in order for that statement to be true. And finally, law of disjunctive inference. Recall disjunction is just an or statement. If P or Q must happen and P doesn't, then this one of the 2 options can't happen, which means that Q must occur. So, if we wanted to apply some of these laws of inference, we can use them to make logical conclusions about given statements. So, looking at these 3 examples we have down here, if I look at the statement, if it's raining, you'll need an umbrella, well, that's a conditional statement, so I can let R represent the statement, it's raining, and U, the statement, you need an umbrella. So if I convert these to symbols, there, we can kind of see how these laws of inference would relate a little bit easier. This is clearly a law of detachment situation of these 3. I'm detaching off that conclusion to make a statement. If the conclusion must follow from the hypothesis and the hypothesis happens, the conclusion I'm making is basically, I will need an umbrella because it's raining. If it's raining, I need an umbrella. It is raining. I will need an umbrella. So I can make that statement. It would be, I need an umbrella. And the law that I'm using is basically law of detachment. Okay. Moving on to the second example. He said, if it's Monday, notice that the hypothesis here, which follows the if, is it's Monday. So if I'm going to convert this to symbols, it's basically, we're hiding here, if it's Monday, he said. That's a statement which is equivalent to he said if it's Monday. He's not sad, so the statement that would follow would be, it must not be Monday, by the law of contrapositive inference. Okay. So it is not Monday by the law of contrapositive inference. Finally, he'll drive or he won't go. Notice that there's a hidden not in here. In won't, he will not go. So when I represent nots in logic, that's the tilde that we mentioned before. He'll drive or he will not go. He goes, which must mean that he drove there, using the law of disjunctive inference.